This is a recording for pre-calculus, and this is 4.8. And so we've done 4.1 through 4.7 and tested on that. But now we're going to do 4.8 and then move into chapter 5 before we have another exam. So this is on applications and models, and our objectives are to solve real-life problems involving right triangles. So that's pretty straightforward for us. Drawing the picture, of course, is going to be the biggest challenge. And then solve real life problems involving directional bearings. And that's like, ships in the sea, planes in the air, and they are a little bit different as we look at those. And then to solve real life problems involving harmonic motion. And so that's like, when things are moving maybe in an up and down motion and seeing what happens there. So we'll start by looking at our first subheading, applications involving right triangles. And the very first problem that we're going to do is just kind of solving the right triangle. Here's a right triangle, here's some information for it, find all the missing parts. Pause this if you need time to write that subheading, and then moving along. In this section, the three angles of a triangle are denoted by capital letters A, B, and C, where C is the right angle, and the lengths of the sides opposite the angles by the letters lowercase a, B, and C respectively, where C is the hypotenuse. So if it's a right triangle, that's kind of our situation that we're having there. So here's our first one. The directive that says solve the right triangle means find all the missing parts. And so when possible, you want to use the given information to find answers. As we move on into non-right triangles, we'll notice that that's not always possible for us either. And so if you want to pause this and just find all of those, I'm finding the side lengths and the missing angle there to the nearest tenth. So if you want to pause this and find those, go right ahead. And then I'm just going to move into solving them. For this one, to find capital B, which is this angle B right here, I know that this is 90, this is 34.2, so really I could go 90 minus 34.2, but eventually I won't be able to do that. So in this case, I'll take 180 minus 34.2 plus 90. And so B equals, or 90 minus 34.2, kind of just to model both of those, 55.8 degrees. So there's B. Then I can find A or C next. And so I'll find maybe A next, and I'm going to use the tangent of capital A. So the tangent of capital A is equal to opposite over adjacent, and so that's A over B in this case. So that means the tangent of 34.2 degrees, so make sure your calculator's in degrees, you're using a lot of radians before, equals A over 19.4. Pretty straightforward to then multiply both sides by 19.4. 19.4, and then we get 19.4 tangent 34.2 degrees is equal to A, and then when we get that approximation, A is approximately 13.2. Now, we could use the Pythagorean theorem to find that missing side. The trouble with that, or the only thing to be cautious of, and of course, if you show your work, it's less of a deal on an exam where you want to get all the points. But if I use A and I've made an error in finding A, then I'm kind of doomed to get C wrong using the Pythagorean theorem. So instead, I personally would maybe just use cosine, and so I know that the cosine of capital A is equal to adjacent over hypotenuse, so B over C. So cosine 34.2 degrees equals 19.4 over C. And, this one only is a little bit more difficult just because the C is in the bottom. Just a reminder, we can multiply by C and divide by 19, or excuse me, divide by cosine 34.2, oops, 34.2, divide by cosine 34.2, and that gives us that C is equal to 19.4 divided by the cosine of 34.2 degrees. And then when we type that in, we'll get what little c is. And so C is approximately equal to 23.5, 23.5. And there's no labels given for those lengths, so we're not going to label them either. I will just comment, in this particular situation, I just figured this myself, you would still get 23.5 if you used that rounded 13.2 and the Pythagorean theorem. And so that's just another comment. Since you're rounding little a, oh, and I did not write that that was approximately equal to, let me fix that, then sometimes you can get a little bit more of an error when you're finding the other parts there. So just be cautious of that as you go. Then moving on to number 2, same kind of thing. Maybe pause this, draw the picture, and then we'll kind of compare our pictures as we go. Let me, I'm going to read it. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. The fire department's longest ladder is 110 feet. What is the maximum safe rescue height? So take a minute, pause this, draw the picture, and we'll compare our answers. Sometimes it helps to check that you have a good picture before you actually do the work. So I'll show the picture, and then if you want to pause it, I haven't done the work yet, and then I'll show the work. So here's my building. And the ladder might be on a truck or something, but we're just going to go from the ground. So I get my kind of little right triangle right there, and 72 degrees is that maximum safe rescue height. 110 feet is the length of the ladder, and then we want to find how high we can have that up the side of the building, so to speak. So pause it again, solve, and we'll compare. So when we set this up, we get that the sine of 72 degrees is B over 110. 110 sine 72 is B, and so B is approximately 104.6 feet. And we do want to label answers as we go. And sometimes, we want to be able to communicate our mathematics. So the safe maximum height, rescue height, from the base of the ladder, because it might be above a truck, is 104.6 feet. Just so that we have that, maybe above a truck or above the ground as we go. Next problem. This one, we maybe have to make a couple of triangles, one picture, couple of triangles. So if you want to pause this, go ahead. I'm just going to work right through this as I go. So let me read it. At a point 200 feet from the base of a building, the angle of elevation to the bottom of a smokestack is 35 degrees, whereas the angle of elevation to the top is 53 degrees. And find the height S S is not my favorite letter, of the smokestack alone. So I'm going to color code my picture a little bit. I'm going to have my building right here. And obviously it has a smokestack at the top. I'm going to put it at the edge just so it's easy. And there's the smoke coming out. Oops, so we know it's a smokestack. And so what I kind of have to think about is I know that I am going to be 200 feet from the base. So, oops, from this point, it's 200 feet to the base of the smokestack. So from my little point there. And I'm going to have, and I'm going to color code these. So to the bottom of the smokestack, I'm going to get this right triangle. And that angle of elevation is 35 degrees. And this is going to be the height of the building. I'm going to call it A. I don't know what it is, but I feel like I'm going to have to figure it out because then the other part I have is to the top of the smokestack. And that was not a great line. There we go. To the top of the smokestack, I get this picture. This angle is 53 degrees. And I want to find S, the height of the smokestack, S for smokestack, I guess. And then on that triangle, I know for the green triangle to the top of the smokestack, then this will be like S plus A. And so that kind of gives me my situation. And then since I color coded these, I'm going to look at the red triangle and I'm going to say this is the opposite and adjacent sides that I know something about. I know nothing about hypotenuses, so I'm not going to use those. But I know for the red triangle that the tangent of 35 degrees is equal to A over 200. So that's something that I know. And then I know for the green triangle that the tangent of 53 degrees is equal to that whole long side that's the opposite. My degrees didn't show up very well. 53 degrees, which is that whole long side, which is S plus A over 200. And so what I'm going to do is I'll plan in yellow. I'm going to get A alone by multiplying by 200. Once I have A alone, I'm going to plug that A stuff in over here, and then I'll just have the one variable. And you know, this is kind of helping me as I do more complex trick things down the road. So first thing, I'll multiply by 200. So 200 tangent 35 degrees is equal to A. And then over here, I'm going to say, okay, so tangent 53 degrees is equal to S plus that stuff over 200. So in place of A here, I'm going to put the 200 tangent 35 degrees. And then I'm just gonna kind of solve all this and see what I get from that. First thing I'm gonna do is multiply both sides by 200 just to get rid of that fraction. And you know, I could have gone about this in a little different way as well, but that'll give me 200 tangent 53 degrees equals S plus 200 tangent 35 degrees, and I want to get S alone, so I'm just going to subtract that. And by doing it this way also, I haven't like gotten partial answers and rounded things so that I lose some of my integrity of my problem as I go. So when I subtract that, I'm going to get 200 tangent 53 degrees minus 200 tangent 35 degrees equals And then just kind of using a calculator to figure out approximately how tall that smokestack is. If you want to pause this and try that, go ahead. Otherwise, it's 125.4 feet. And so the height of the smokestack, the height of the smokestack is approximately 125.4 feet. My 4 did not turn out well, so I'm going to just rewrite that. Okay, and so that is number 3. And, personally, I find these to be just kind of a fun thing to do. So go ahead if you want to pause this to try number 4. I'm gonna just keep working through to set it up, and then I might do my work and then show that. So it says a swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted, so the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. Find the angle of depression in degrees of the bottom of the pool. So when I draw this pool, I'm doing a vertical cutout. I think of it long ways as I kind of think about that in my head. So, the whole pool depth, um, the this would be that 1.3, and then it gets deeper as it goes. That's the best I'm going to get there. So we have 1.3 feet, right, or meters, excuse me, right there. We know it's 20 meters long this way. And let's see, and 4 meters at the deep end. So I know this is 4 meters. And I wrote that a little bit further away because I also know this is 1.3 meters. And then if I take 4 minus 1.3, that's 2.7 meters. So I kind of know that little piece of this as we go. And then what that's going to give me, I want to find the angle of depression in degrees of the bottom of the pool. And so that angle of depression is going to be this angle theta right here. And this is my right triangle. And I know that 2.7. I'm just going to keep going then. And so in this one, I know from the top part, if that's 20 up there, this is also 20 meters for that piece of the triangle. It's a little upside down, but that's okay. And I'm going to use tangent again. So tangent of theta is equal to opposite over adjacent, so 2.7 over 20. So I'm going to say theta is approximately, or is equal to, before I do that, I'm going to say tangent is equal, or theta is equal to the inverse tangent of 2.7 over 20. Good to practice that. We haven't done things like that for a while. And then when we find that, we get 7.69 degrees, and that is in degrees as we look at that one. So kind of fun to kind of be able to do that as we go. And now let's move into kind of this concept of bearings and direction. And so this is trigonometry and bearings. So this is very old information because, or, not dated old, but old because, people have been sailing the seas for a long, long time. And so when people are surveying and navigating directions, great, we're going to go at a 60-degree angle, but from where? And so bearing measurements are using an acute angle or path that makes, we use kind of that northern star or the north arrow the arrow pointing north on a compass, and we go from one direction or another from there sometimes. And the only thing we have to be careful of is we also go in airplanes, and airplanes go um, clockwise from north always. And so then they just go, they can go up to, well, 360 degrees, but why would you? And so that's something that we have to be cautious of as we go. So bearings. Now we want to say, okay, I'm going to start at point A. I'm going to get a bearing and a direction. So not just a regular angle, but actually a bearing in relationship to north, south, east, or west. So just a few little like just reminders. Make sure north, south, east, and west. And so that's the first thing to know. And when you give a bearing, you start with north or south first, and then you give a degree, an angle in degrees, and then you go east or west. So that's an important thing because think about navigation, and we want to always kind of be starting on that north arrow, and south is just 180 degrees from there as we go. And so bearing, it has a fixed north-south line, so that's where we're always kind of going from to begin with. So this one that's south 35 degrees east means that it's 35 degrees east of south. So, I would have a good note about that because I've had students before, start with east and west, and then things get kind of mixed up as we go. Because think about the fact that, and I'll slide this up a little bit, this is a 90-degree angle. And so if this is south first and then 35 degrees like that, that would be different than if you went east first and then 35 degrees like that, because it would be this far. The only time that's going to be right is if you're directly, you know, southeast or east south, which was be a 45-degree angle. So be cautious of all of that for bearing. And I am going to say you should draw these three pictures and these labels. So south 35 degrees east, which is 35 degrees east of south. So the way you want to think about that, because you're going to draw pictures, is you go south, then you go to the east 35 degrees, and this is the line you're traveling along as you go. This one is north 80 degrees west, so you kind of look at north, and then you go to the west 80 degrees, and so you're traveling along that line as you go. And then this one, this is the one you can make a mistake on and still be right. So if we're going north, and then from there we go to the east 45 degrees, we're traveling along that arrow right there. So that is for shipping, I'll say shipping, and not like UPS, land to air shipping, and FedEx and things like that. But this is like in a boat shipping. And so then the other thing I'm going to make note of, because I don't really remember that they say anything about it here on these slides, and that is air navigation. Air navigation is different. Navigation is different. There we always, for that bearing, is the degrees clockwise, from north. So, um, for air travel, you can still think of that little compass kind of thing, but now it's always from north and then around. So if our plane is actually traveling out that way, it would be this big angle that would be from north, so something over, what would that be, 270 or something, 285 or something, 285 degrees would be that air navigation bearing as we go. So what I'm going to leave you with today is a problem, and all I want you to do, and I would hesitate to, um, solve this until you know the problems, right? Or if you feel confident, go ahead and do it. But this is one of those kind of problems. People sometimes talk about trains and ships and things like that. And okay, so what I'd like you to do is draw a picture of this situation and kind of see what's happening there. And then in the next recording, we'll kind of look at it and see how things went. So set up this situation. If you feel ultra confident, go ahead and do it. Otherwise, in the next recording, we'll look at that.